Welcome to this learning series entitled A Journey into Music and Sound with Math, Engineering, and Matlab. So, you might be asking, why in the world did he do this series? Well, many times what happens is students in middle school and high school are interested in music as a career. They may want to be, let's say, a singer, a rapper, a music producer, all the very high profile type jobs. However, what they may not know is that they can be a mathematician, a computer scientist, an electrical engineer, or computer engineer, and very much be a part of the same music industry. Now, why is this? Well, most music today contains or utilizes some sort of electronic equipment. This utilization can be while music is being created, it can be while music is being stored, or it could be while the music is being regenerated, or it could be all three according to the type of music. To show the connection, let's start with the following example. In this example, I want you to consider a speaker. This speaker has a cone, okay? This cone moves back and forth. When the cone moves back and forth, it creates air sound waves consisting of high and low pressures. And it is these air sound waves that create sound. Okay, so let's now put a mathematical or look at this in a mathematical way. Well, back to the speaker again. We may graph the movement of the speaker, that back and forth movement, using that mathematical function called sine function, which you may or may not be familiar with. So at the top here, what we are saying is that the speaker is moving out, and by the way, on my x-axis here I have time, and on my y-axis I have displacement. So the speaker is moving outwards, okay, and then it's moving inwards, and then moving outward again, okay. Now that movement back and forth again is what creates the sound. The part here where we have 0, it doesn't necessarily mean the speaker isn't moving. What it means is this is an equilibrium position. What it means is if the speaker was not moving, this is the position at which the speaker will assume. And so in other words, this is where the speaker would stand in terms of our math function here, or our representation in the graph here. This is where the speaker will stay. And we call that the equilibrium. Now, again, we said that when the movement of the speaker goes in and out, that back and forth movement, it creates those vibrations, and those vibrations create sound. So that back and forth movement, which creates the sound, we can also map this or graph this using the same sine function. And we can use the sine function equation for this, which is y is equal to a times sine omega t. We can use that to represent that back and forth movement, or and the sound level of this being generated by the speaker. For the sine function here, a sine equation, y is equal to a sine omega t. Let's talk about what each one of these variables mean. Omega, which is the angular frequency, is equal to 2 pi times f. As some of you may know, pi is equal to 3.14 and a whole lot of numbers after that. But for the purpose of making this just a very simple introduction, we're just going to look at it as being 3.14. Okay. A is the maximum amplitude for the specific function that we're dealing with. All right. So the maximum amplitude in this case here would be 1. And the minimum amplitude in this case would be -1. All right. We also have F, which was a part of our omega equation up here. That F is equal to frequency. And frequency, by the way, is measured in hertz. You may have heard the units of hertz before. Frequency is actually equal to 1 over capital T, where capital T is equal to the period. And what is the period? Well, the period is equal to one cycle of the sound wave or the sound level. Or if we want to put this in terms of something we can grasp a little bit easier, that's one cycle of the speaker moving out, back in, and then returning to equilibrium. Okay, so that's your one cycle there. And we can measure all of this again using our time and our amplitude. So music produced by a speaker and instruments like trumpets or clarinets or drums are what are called continuous signals. So if we go back to our previous slide here, you'll see that for every single value in between 1 and -1 for this entire sine wave, there is some amplitude associated with the time in here. So for every instant in time, there is an amplitude that's being mapped. Today's music, however, is stored in a digital format. If the music is produced by a non-electronic or electric instrument, that music starts out as a continuous signal. It then has to be changed into a discrete signal before being digitized or turned into a digital signal. Now, for the purpose of our presentation here, our introduction presentation, we're not going to get into the digitization of the signal. We're just going to talk about the continuous and the discrete. Thus far, we've talked about the continuous in the previous slides and so forth. So let's look at how we would take our signal now from being a continuous signal to being a discrete signal. In order to transform our signal from being a continuous signal to a discrete signal, we have to do two things. We have to sample the signal and we have to quantize the signal. Okay, let's talk about what that means. And we'll talk about that by looking at this particular regeneration, if you will, of a sine wave. What you'll notice in this sine wave is that each one of these circles here, by the way, represent a specific instant in time for which we captured the amplitude. And what you'll notice also is that in between each one of these circles here, there is nothing in between. Okay, there's nothing in between. So we've captured a sample here, we've captured a sample here, 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 so on and so forth, all the way out until we finish our one cycle. Now, to make this just a little bit easier to grasp, let's go ahead and change this from being just simple circles here to what we like to call sometimes stem or lollipops. Okay, and so now you can see here now that we have the same circles that we had from before on the previous slide, but now we've added some lines to them. Okay, the time between each one of these lollipops here is what is called the sample period. Okay, that's what's called the sample period. That sample period means that at this specific instant in time, let's say here, we went and captured what the amplitude was. At this specific instant time, went and captured what the amplitude was, so on and so forth. Okay. Now, if we were to take that sample period and take the inverse of it, we would end up getting what's called a sample frequency. Now, this is a term that we're going to have to remember for a little bit later on when we actually start to use Matlab to dissect music and take a look at it. Okay, so just to remember that term, the sample frequency. So we captured the amplitudes at these specific instances in time, as I indicated. Now, so that's a sampling portion in order to turn our continuous signal into a discrete signal. Now, what we also have to do is take the continuous signal's amplitudes and quantize them. Well, what does it mean to quantize? Well, what we do is we make each of these values or each of the amplitudes from the original continuous sine wave, and we have it what we do is we take it and we round it to the closest discrete value of a set of predetermined discrete values. Okay, so each one of these amplitudes here, for each one of these instances in time that we capture the amplitude anyway, we have rounded these values to some discrete time, or pardon me, a discrete amplitude of a set of predetermined discrete values. And by doing that, we have quantized the original continuous signal. And because we're able to do both the sampling and quantizing, we can then digitize the music and then be able to use that, let's say, on a computer, or we can store it on a memory stick, or we can play it from a CD player, or we can play it from an MP3 player, so on and so forth. Okay? All right. So now we've captured those bits of information and we want to store them. So when we store them in memory, examples of when we store them in memory, discrete values, we store them in areas of memory where the areas of memory contain the numbers or the amplitudes that are associated with the specific instant in time in which we captured them. So we can store them in what are called vectors. So when we get to the programming part of this entire series, we're going to talk about vectors. For the purpose of just making this simple right now, we're going to represent a vector by the equation here where we have y is equal to, we have the square bracket, and then we have a number, another number, so on and so forth. Each one of these numbers here again represents, pardon me, a quantized value. Okay, so each one of these numbers represent a quantized value. So y is a vector containing the discrete amplitude values. Now f of s, which we're talking about the sampling frequency, what happens is when we store this information into our digitized form, we also need to store the sampling frequency so that when we're having our digital player or we're digitizing the music, so that we can know in the future how soon we need to output this specific amplitude, this amplitude, this amplitude, this amplitude, so on and so forth, in order to regenerate our music so that it sounds the way that it sounded, or as close as possible anyway, sound the way that it sounded when it was just a continuous sound coming from, let's say, that trumpet or that drum or those or the clarinet. Okay, so all of these parts are important. And we'll talk about that, like I say, when we actually get to the actual practical application of this all. Okay, so if we were to say that the digitized music was what is called CD quality, there are certain characteristics that it must meet. The sampling frequency, the sampling frequency has to be 44 kilohertz or 44,100 hertz in order for it to meet sampling frequency, or pardon me, or CD quality. There we go. In order for it to also meet CD quality, the number of quantization levels has to be equal to 65,536. This is equivalent to 2 to the 16, where 16 in this case is the number of bits that are being used to represent uh, the numbers when we digitize them. But as I said, we're not going to get into the digitization because that's a little bit outside of the scope for right now. Okay, so just keep these in mind for when we get to the practical example. All right, so this is the end of series part 1 of the series on a journey into music and sound with math, engineering, and Matlab. Please do look for the future series on my YouTube channel. If you have any questions, you can always contact me through my website. My website is www.clydeletsome.com. Again, that's www.clydeletsome.com. Please do come back for part 2 of this series.